Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
1 AG 84. Richard Dedekind was sin and was sollen die Zahlen. Introduction. Richard Dedekind was sin and was sollen die Zahlen. What are numbers and what should they be? Represents a watershed moment in the history of mathematics, the rigorous foundation of arithmetic. This essay undertakes a systematic, section-by-section examination of Dedekind's work, probing its central claims, methodologies, and underlying arguments. Its objective is a critical evaluation of the conceptual landscape Dedekind painstakingly constructed, along with an assessment of its enduring impact. This analysis prioritizes the internal logic and coherence of Dedekind's exposition, while considering the historical context as it bears directly on the validity and interpretation of his claims. Our focus is on the substance of the work's claims, their genesis, and their influence, providing a deep evaluation of this foundational text in the construction of modern mathematics. Section 1. Defining the positive whole numbers. Dedekind begins by grounding his construction in fundamental concepts. These are the foundations upon which the entire edifice of arithmetic will be built. He asserts that the positive whole numbers constitute an independent object of study, one that can be precisely defined and understood. The initial focus rests on defining a system, which in Dedekind's context corresponds to any collection of objects. The core concept introduced, essential to the whole construction, involves the notion of a chain. A chain, in Dedekind's terminology, is a system of objects such that if an object belongs to the system, then its image also belongs to the system. This notion of an image, or successive successor, acts as the primitive operation, the foundation for defining addition. Dedekind proceeds to define the positive whole numbers as a system which satisfies several postulates. These postulates emphasize the existence of a unique initial element, the number 1, and a function that maps each element of the system to its successor. The critical aspect and the core claim of this early section is from these simple starting premises, the entirety of arithmetic, including addition and multiplication, can be constructed. Critiques of this framework center on the circularity inherent in defining numbers in terms of functions, particularly those concerned with the implicit use of the very concepts being defined. Such criticisms, however, diminish in their sting when considering the clarity Dedekind offers in this framework. His explicit framing of these primitives offers a concrete starting point that earlier attempts at formalizing arithmetic lacked. Section 2. The concept of the infinite. The introduction of the concept of the infinite represents a crucial extension of the foundational ideas. Dedekind defines an infinite system as a system that is similar to a proper part of itself. This means there exists a one-to-one mapping from the entire system onto a subset of itself. The core of this section resides in this definition, which departs from earlier, often metaphysical, understandings of infinity. Dedekind's claim here is that infinity can be captured in a mathematically precise manner. The implications run deep. This enables a rigorous treatment of concepts, such as the existence of infinitely many natural numbers, which provides an entirely new framework for understanding the infinite. This definition stands in stark contrast to the intuitive or philosophical notions of infinity prevalent at the time. Furthermore, it opens the door to considering different sizes of infinity, which were later expanded upon by Cantor and which revolutionized set theory. Critics sometimes raised the question of whether this definition of infinity truly captured the essence of the concept. Others scrutinized the underlying axioms about how similarity is defined, arguing that these axioms may be taken for granted in the definition. The beauty of Dedekind's argument, in this regard, is in the reductionist approach. He makes the concept of infinity both mathematically precise and accessible. Section 3. Defining the natural numbers more formally. Dedekind refines his definition of the natural numbers, building on the earlier postulates. He introduces the idea of a simply infinite system. This kind of system is characterized by its similarity to the set of natural numbers, with a unique initial element and a well-defined successor function. The key assertion here is that all the properties of the positive whole numbers can be derived from this abstract structure. This involves demonstrating that the familiar arithmetic operations, like addition and multiplication, can be defined and their corresponding properties proven within the system. Dedekind emphasizes the abstract nature of these numbers. He contends that the specific objects that represent the numbers matter less than the relationships between them. The core claim centers on formalism, the ability to treat numbers as structures governed by well-defined rules. The advantage is that the definition removes the need for a specific, physical instantiation of each number. This has the result of enabling arithmetic to be separated from any specific instance of physical objects. Criticisms of this approach centered on its abstract nature. Some argued that it lacks the intuitive appeal of more concrete approaches. Dedekind's approach, however, offers a framework with a high degree of rigor and generality. Section 4. The definition of addition. The definition of addition, constructed within the framework previously described, represents a critical step, serving as the building block for further algebraic operations. Dedekind defines addition through a recursive process. If A and B are numbers, then A plus B is defined as the successor of A plus the predecessor of B. This ensures that the fundamental rules, such as the commutative and associative properties, are valid by construction. The essential argument here is that addition is not a primitive operation but is rather a defined function within the simply infinite system. The power of this formalism lies in the fact that the same structure can be applied to define other operations. The proof techniques employed, based on mathematical induction, are also presented in detail, ensuring complete rigor to this operation. The significance of Dedekind's definition is that it removes any ambiguity from the process of addition, ensuring a clear and consistent understanding. Critics sometimes claimed this definition was overly abstract, a point Dedekind acknowledges, but defends in its utility as a unifying framework. Section 5. The properties of addition. Dedekind meticulously demonstrates the properties of addition within the formal system. He establishes the commutative property, which asserts that A plus B equals B plus A. This shows that the order in which addition is performed is irrelevant. He proves the associative property of addition. The combination of three numbers will be the same irrespective of the order by which they are combined. This ensures that the results hold regardless of where parentheses are inserted. The central claim of this section is that these fundamental properties are theorems, derived logically from the postulates and the definition of addition. This constitutes a proof system of arithmetic, where all the rules emerge from first principles. Dedekind's insistence on rigorous proof, avoiding any reliance on intuition or assumptions, sets his work apart. The core assertion here is that arithmetic is not merely a set of rules that are conveniently true but can be explained logically. Those who criticize this approach find the proofs long and laborious. The value lies in the completeness of the mathematical explanation. Section 6. The definition of multiplication. Building on the foundations of addition, Dedekind constructs the definition of multiplication. He defines multiplication as a recursive operation based on addition. The product of a number A and a number B is, by the definition, equivalent to adding into itself B times. This definition allows Dedekind to derive the properties of multiplication, similarly to how he showed the properties of addition. The essential claim is that, by extending the logic of addition, multiplication arises naturally from the fundamental axioms. Dedekind uses definitions of both addition and multiplication that are grounded in the concept of the successor function. This ensures that multiplication is consistent with addition. The beauty of Dedekind's approach is that he clearly shows the relationship between the various operations. Critique focuses on how the recursive definitions may lack intuitive appeal. Dedekind would counter that mathematical precision surpasses mere intuition. Section 7. The properties of multiplication. Dedekind proceeds to prove the properties of multiplication. Mirroring the method used for addition, he demonstrates the commutative property, which shows that the order of multiplication does not matter. He proves the associative property of multiplication, that the parenthesization of multiplication is irrelevant. He establishes the distributive property, which relates to addition. The central claim is that the fundamental properties of multiplication follow logically from its definition. This underscores the cohesive nature of Dedekind's framework, where complex concepts arise from simple, fundamental axioms. This section offers a complete and rigorous treatment of the basic axioms of arithmetic by the time Dedekind has finished. Criticisms focus on the laboriousness of the proofs. The significance lies in the completeness of its internal arguments. Section 8, the principle of mathematical induction. Dedekind gives a precise formulation of the principle of mathematical induction, a cornerstone of the proofs he constructs in his work. He states the principle in a form that can be applied to any property possessed by natural numbers. This principle states that if a property holds for a starting element and if, whenever the property holds for a given element, it also holds for its successor, then the property holds for all elements of the system. The core claim here is that induction is not an axiom but a consequence of the definition of a simply infinite system. This clarifies the logical status of mathematical induction, demonstrating its connection to the underlying structure of the natural numbers. Dedekind's systematic treatment of induction provides a precise means of proving statements about natural numbers, which is essential. This section makes it possible to confirm the validity of any property based on the rules of arithmetic. The significance of this section is the formalized rules for the use of induction. The formalization of this principle makes it possible to avoid the pitfalls of intuitive methods. Section 9, Applications and Extensions. Dedekind concludes with applications of the framework that he has built as well as its limitations. He outlines the possibility of extending the system to encompass other number systems, such as the rational numbers. He emphasizes the abstract and general nature of his framework, pointing out that it is not limited to the study of natural numbers. The underlying assertion is that his approach provides a robust foundation for the development of all arithmetic. Dedekind's work set the stage for the development of set theory and other foundational areas of mathematics. He stresses the importance of rigor, showing a path towards a complete and formalized understanding of arithmetic. Critics argue that this approach may not be well suited for pedagogical purposes, as it focuses on abstract formalisms. The work's impact rests on the generality and the rigor which Dedekind provides. Conclusion. Dedekind's sind und sollen die Zahlen presents a comprehensive and groundbreaking approach to the foundations of arithmetic. The work's success is visible in the power of his arguments. Dedekind's systematic approach demonstrates that the natural numbers can be defined rigorously from fundamental primitives and that all arithmetic operations can be constructed from these simple foundations. The critical examination reveals the elegance and precision of his approach. The systematic section-by-section analysis underscores the rigor of his arguments. Dedekind's work has fundamentally changed the way mathematics is conceived. His focus on the abstract and the formal set the stage for the development of set theory and the rigorous formalization of mathematics. The impact of his work is undeniable and has profoundly influenced mathematics. Dedekind's enduring legacy lies in his construction of a solid, logical basis for arithmetic, and in the profound influence he had on modern mathematical thinking.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.